Okay, hello everybody. Hopefully all of you are doing okay. So this is the first of my live streams. My plan is to do a live stream on a Sunday night, a Monday, Tuesday, Wednesday and Thursday. So basically that's 5 evenings a week. I suspect not many people are going to be doing stuff on a Friday night or a Saturday night. And so yeah, the plan is there's going to be a live stream where I go from 7:30 till 8:30. And this means that between 7:30 and 8 o'clock, I think as it says just beneath me, we're going to be doing GCSE for the first half an hour, and then for the second half an hour there's going to be A-level. So just to for anybody who's watching at the moment, if you're doing A-levels then maybe come back at 8 o'clock. But I just want to show you something. So what you should find is if you go to my website, I've got GCSE Physics Online, and I've got A-level Physics Online as well. Now on the GCSE site, if you go to gcsephysicsonline.com/live, or just click on the live icon up here, it brings up this page here, and this then has what's going to be in the live stream tonight. So we can see we're going to be doing some paper 1 revision today. We're going to be looking at isotopes and resistors. We're then going to be doing questions 1 and 2. And that's basically the kind of plan for tonight. So this means that if you want to, you can download the material in advance. You can have a go at the questions, and that means when it comes to the live stream, you already know kind of the questions which I'm going to be going through. So that's basically the plan, and I'm going to sort of populate this for the rest of the week tomorrow. For A-level, I've got exactly the same thing. So this is a-levelphysicsonline.com/live. If you've just joined the stream just now, you'll find that there are some questions here. These ones happen to come from my daily workout book, and basically you can download these, and you should then find some questions. So the questions are related to dates in the book, but if you're doing A-level and you're watching this live, you could go and download this PDF, have a go at some of the questions, or at the very least read through them. And that means when it comes to 8 o'clock in the session, it's not just completely random questions, but of course I will be answering your questions throughout as we're going through the stream. So that is the A-level physics one. But for GCSE tonight, we're going to be doing stuff for AQA paper 1. But, and I can see there's some stuff in the chat about, am I going to be doing OCR? Pretty much everybody doing GCSE is going to be doing exactly the same content. So you need to know about isotopes. You need to know about resistors in parallel and series. And so the content I'm going to be going through will be relevant for everybody out there. Also, it would be great to know in the chat, and by the way, there is obviously the chat in the live stream. If everybody could press the heart button, that would be amazing. And you'll notice that you need to be a subscriber to chat. So that's a very simple thing. Just subscribe to my YouTube channel, then you can put stuff in the chat. Kensfer, what is the main difference between all the exam boards? That's a really good question. Basically, the content is going to be very, very similar. About 95% of the content is the same at GCSE and A-level. The main difference is really the structure of the exams, as in which topics you might have in paper 1 and paper 2. But really, if you're doing GCSE, the content for AQA, OCR and EdXL is pretty much identical. And it's maybe only a little bit different if you're doing IGCSE or you're doing exams in Wales, but 99% of that content is going to be the same, because it doesn't matter which exam board you do at GCSE, that it gives you all the skills that you need to go into A-level physics. Right, so GCSE then, we've got about 25 minutes left. The questions tonight have come from this paper here that I've written. So this is a load of GCSE style questions. So the kind of thing that I'm sure you're pretty used to. This one is a paper 1, and this is a practice paper that I've written. So it's not a predicted paper, because nobody can really predict what's going to come up. But I know that if you do all of these practice papers that I've put together, that will cover pretty much all the questions that could be asked in your real exam. Potentially. So this one here, again, you can download it from my shop, which is physicsonline.shop. You can see a link to that probably beneath the video. There's links to it in the description. And basically, we're going to be doing a couple of questions. Now this is just one paper out of 12 that I've written. So I've got 6 paper 1s and 6 paper 2s. And I've just called them alpha, beta, gamma, delta, epsilon and zeta, just to show that there's 6 different versions. So it's this paper here we're going to be doing today. Tomorrow we're going to be doing some paper 2 stuff. And then we're going to sort of look at these papers over the next few weeks. And so basically in the paper, if you do decide to buy it, you'll see a load of questions. And the other thing is that... oh yeah, sorry. Another thing I probably should say is that what I'll do is, if anybody kind of spams the kind of comments, all I'll do is just delete from the channel. Hopefully that's all right. Okay. The other thing I want to show you here is that by doing these 6 practice papers, then that means that you cover all of the content that's covered in GCSE. So, for example, we're going to be doing a question today. If I just zoom in a little bit, on atoms and isotopes, and you can see that if you did the second paper, there's another question about atoms and isotopes. There's then a question about atoms and nuclear radiation over here, and these are just the AQA spec points, nuclear fission and fusion. You can see how in each paper I've got similar questions that cover all of the points in the spec. Vegetaval, can I share a link for that please? Yeah, basically there's a link in the description to this live stream, and if you go to gcsePhysicsOnline.com/live, you'll be able to find a link to actually get hold of this. Okay, so let's just start with some stuff. And again, if you want to, in the chat, put down your answers, please feel free to do so. So the first question is about the structure of the atom. So this is going to be useful if you're doing GCSE chemistry or GCSE physics revision. You basically have to know the same stuff. But in physics, we tend to actually look inside the atom, whereas in chemistry, we just think about the way that atoms sort of behave with one another. So how many times bigger is the atom than the nucleus? So we probably have this kind of mental model that we've got this kind of nucleus in the very centre. Often there's different ways of representing it. You might have different colour circles to show the neutrons and the protons. And then a long way away from this is where we have this kind of cloud of electrons. Okay, so this is a very simple picture here. That's maybe a helium nucleus. In my videos, if you've watched anything I've done before, you'll notice that I do tend to use a lot of Lego, where I just use these small bits to be the electrons, and then we've got protons and neutrons in the middle. Okay. Now the thing is, this is just a model, and what we've really done there is overestimated how big the nucleus is, because it's very hard to draw it otherwise. So for this one over here, the answer is about 10,000 times bigger. Now, what that means really is that, I suppose really if I'd drawn an atom this big, the nucleus, even if I just put a dot here, that really wouldn't have been to scale. And so really what I'm trying to sort of emphasize here is just how much empty space there is inside the atom. And that's why when Rutherford, along with the other people he worked with, when they did their experiment with the gold foil, most of the alpha particles, these kind of positive particles, most of those things went straight through, and only a very, very small number were actually deflected by that nucleus. And you do need to know that, because in the specification, which I'm just going to get for you. So I do have a download that you can get on my website, again at GCSE Physics Online. I'll probably put the everything in like the description. But I've got a revision guide here that goes through all of the spec points. Now you can only get it as a digital download because I can't print it out due to copyright restrictions. But where are we? We've got energy, we've got electricity. Let me just see what the actual course says. Okay, so yeah, so basically in the actual specification and what AQA say is that we call that the radius of an atom is about 1 × 10⁻⁻10 meters, and the radius of the nucleus is about 10,000 times smaller. So this first question was purely a fact that you should remember that you just, I suppose, learn by actually having a look through the AQA specification. But this is one of the kind of key learning points. So the nucleus is about 10,000 times smaller than the atom itself. Okay, the next one, a little bit more complicated. Again, if you want to in the chat, if you're watching this live, state the name of the scientist who improved Rutherford's nuclear model of the atom by discovering that electrons orbit the nucleus in shells or energy levels. So I suppose what Rutherford really found was that we had this dense positive central nucleus, and then we had electrons around it. Later on, they also then discovered that we have neutrons. So it's not just protons, there's neutrons and protons in the nucleus. And then, yes, we've got, by the way, people, capital letters. You know, if it's a name, you need to start with a capital letter. Niels Bohr, B-O-H-R. And I think so far, I think most people have just spelt it all in lowercase. Somebody else mentioned Thomson. J.J. Thomson was actually the person who discovered the electrons. Is that right? But yeah, it was Bohr, Niels Bohr, who basically realised that we have electrons existing not just as a cloud, but actually in distinct energy levels. Okay, and again, this is why when you've been doing stuff in chemistry, you might look at the fact there's 2 electrons in the inner shell, there's 8 in the next one, and so on. So the electrons don't just exist anywhere. They can. Oh yeah, sorry. Plum pudding model was J.J. Thomson. Yeah. Okay. Right. So the next bit, according to this model, the distance between an orbiting electron and a nucleus can change. How does that change occur? So how is it that an electron can go from one shell to the other? Now, what we tend to do is we kind of have a diagram like this, but it's a little bit difficult to see. So a way that we can actually represent this, if I'm just going to turn this over, is we often just think about maybe the inner shell and then the shell above it, or the energy level above it, and so on. Okay, so what we're doing is we're just taking a small amount, effectively we're taking like a small kind of segment of those lines, and what we can show is that electrons can maybe exist in what we call a ground state, which is when they're really stable, and if we excite them somehow, then they can move up to a higher energy level, and then they'll lose energy as they drop back down to the ground state. Now, basically what happens is we have a little packet of energy that can be absorbed by this electron, and then it jumps up to a higher state, and then as it jumps back down again, it then releases that little wave of energy. Okay. Now it could be that we've excited something, maybe if you heat something up, if there's a really high electric current or something like that, and really what we have is we have maybe some light or some X-rays or infrared or some kind of electromagnetic radiation which excites the electron, and then as it drops back down it emits that small packet of radiation. So according to this model, the distance between the things can change to describe how this change occurs. So what you can say is that, and again, I've got 3 marks here, so I want to get kind of 3 distinct kind of points. And again, this kind of stuff at the moment, although this is based on one of my AQA practice papers, the actual physics is going to be useful for pretty much everybody. Okay, so what we can say is that an orbiting electron could move to a higher energy level, and this is going to be further from the nucleus. So we've basically said so far that it can change. So an orbiting electron could move to a higher energy level, and the higher energy level is going to be further from the nucleus. And basically this occurs when it absorbs, and I always, it's a B for absorbs, isn't it? And this is when it absorbs electromagnetic radiation. Right, sorry people, I'm just going to ban a few people. Okay, right. Hopefully that's most of the kind of the spam gone. Okay, so basically it could move to a higher energy level, and it's a higher energy level which is going to be further from the nucleus, and that occurs when it absorbs electromagnetic radiation. So, so basically that's one way that that change could occur. So, yes, so maybe a mark for that, a mark for that, and a mark for that to get 3 marks in total. Okay, right, let's go to another question. Here we have some data about 4 different things. We've got substance A, B, C, and D. If anybody wants to have a look at this question, state the 2 isotopes of the same element. So we've got elements or different substances A, B, C, and D. Which of these 2 are the same element? And so this question, even though it's in a physics paper, this is really a question about kind of sort of logic, you know, looking at the table and the table of data. And I think that's what's important, is that there are so many questions based on data that you're given in the exam that you have to interpret really quickly. Well, if we've got isotopes, what do we mean by an isotope? Well, an isotope is just something that is an element which has the same number of protons but a different number of neutrons. And everybody there seems to be saying so far, which is brilliant. Plim, Abdullah, Catherine, Kensfer, yeah, loads of people there, Zane, Jim, all getting A and C. And for this one here, this is just a state question, so you just need to actually write down what the answer is. You don't need to explain anything. So A and C both have 7 protons, whereas B has 8 and D has 9. And it's the protons that actually define the type of element. Okay, explain the answer to this. Well, I guess we really just want to sort of write this down as clearly as possible. So what I would say is that A and C have the same number of protons, but a different number of neutrons. Okay, and then I might just maybe kind of just add a small sentence afterwards. They are isotopes of the same element. Okay, there we go. And of course, yeah, if they've got the same number of protons, then Catherine, they're also going to have exactly the same number of electrons as well. Okay, do you need to mention the name of the actual element? You don't, because in physics, you don't get given a periodic table as part of the exam, and you're not expected to remember the number of protons of the first, or the first 20 elements, or the first 117 elements. So you don't need to remember what this is. Of course, if anybody out there knows what it is, if it's got 7 protons, who knows in the chat which element that is? Okay, I think probably a lot of you are going to get this quite soon. Okay, nitrogen, yes. So what we have there is nitrogen. Normally, I think it's 7 protons and 7 neutrons. And yeah, all of you, you're going to be getting grade 9s, I'm sure. All of you seem to be doing pretty well. So yeah, or either that or you're all kind of A-level chemists. So yeah, you don't actually need to state which element it is. If you know it and you're 100% sure, then it's not going to do any harm. But really the marks for this are gained by the fact we're looking at the number of protons, and that means it's the same element, but they've got a different number of neutrons. So they're the kind of things that are important. Okay, the last one then is a suggest. And these ones here are where students often get a little bit confused. Now, I would say that the suggest questions are easy marks, and these are basically common sense. So every time you see the word suggest, just think about using your common sense and think, you know, what would be a sensible thing here? So basically, our knowledge of the atom is evolving and improving, and we often have large international teams making these discoveries. So, for example, stuff at the moment, things like the Higgs, that's been discovered in the Large Hadron Collider, and that's a massive thing. So, suggest a reason why it's not just maybe one person in the lab fiddling around with stuff. Why is it we need to have like such big, expensive things? We might say, for example, that although technology is evolving, why is that? Probably a better thing to say could be maybe to do with the cost. So you might say that the cost can be shared. So that's kind of one thing. Maybe to make sure there are no errors, that's a good one, yes. You can have lots of people checking and double checking. Broader resources. So yeah, you just want to be really clear about, you're talking about the resources in terms of maybe the computing power that you need, the money to run stuff, the number of scientists to actually look at that data. Peer review, yeah, that's another one. That's really important so that people are actually checking other people's results. And often now, the actual energy, to maybe kind of actually smash apart, the kind of neutrons and protons and the kind of bits inside the atom, we need really, really high energies to look at these really, really small particles. And therefore, we need to have massive, expensive things. And there's a huge amount of data. So yeah, those are kind of things that you could talk about. Right, the next question then is about resistors. And this one over here, you're given 3 resistors, A, B and C, 20, 10 and that one there's not labelled. Calculate the total resistance of resistor A and B if they're connected in series. So I'm sure most of you could work this out really, really quickly. So what is a combined resistance of A and B in series? Now, something that you can do, even though it doesn't tell you to, is just draw a little bit of a circuit diagram. So we've got resistor A and we've got resistor B. I'm going to put the numbers down. So resistor A is 20, resistor B is 10. And if we have resistors in series, the total resistance is equal to their individual resistances added together. So 20 ohms plus 10, so that's 20 plus 10, which is 30. And therefore my answer is 30 ohms. Okay, excellent work from everybody. These questions aren't too bad. But again, it's only 1 mark. You can do this in your head, but it's always worth, kind of, even though it's a simple thing, just making sure you don't get any like silly mistakes. Yeah. Right. Describe how the combined resistance would change if the same 2 resistors were connected in parallel. Now, I know that somebody's already actually worked this out. Now, for AQA, you don't actually have to be able to calculate resistors in parallel. So we've got a 20 ohm and a 10 ohm. But now what we have, the total resistance would decrease compared to when they're in series. Excellent answers that people are putting in, by the way. So describe how the combined resistance would change. We can basically say that it would be lower. Okay. Now for this one, it's only a describe question. You don't need to explain why that is. We're just going to describe what happens, and it goes from maybe 30 ohms to a much lower value. Some people have already said, and this is really good that people are using some of these equations, how you've got, one of them is 1 over RT is equal to 1 over R1 plus 1 over R2. The other one is that RT is equal to R1 R2 over R1 plus R2, which would then be, say, 20 times 10 over 30, which is going to be 200 over 30, so that's 20 over 3, which is 6.67, or 6.7. Now, you don't need to know that if you're doing A-level, and I know some of you are here for the A-level stream quite soon, that will all kind of make sense. But effectively, when the 2 things are one after each other, the total is 30. When they're side by side, there are more paths for the electrons to move through that circuit. That means the overall resistance is lower, and therefore they'd have that value there. But you don't need to have any of that. You just need to say it would be lower. Right. We then have this question, and I think label diagrams are really important. The student has got these resistors. They've got a battery, ammeter, voltmeter. Describe how the student could determine the resistance of resistor C. So we want to know, if you were given a resistor, but you didn't know its resistance, how could you work out its resistance? So the first thing I'm going to do is a circuit where we've got a 9-volt battery. So this is my battery. We've got an ammeter, which is going to go in series with resistor C, like this. Okay, and then in parallel across that, we're going to put the voltmeter. Okay, that circuit, this is my prediction, is that there will be a question for 1 or 2 marks where you've got to put ammeters or voltmeters in series or parallel. So my prediction is there will be a question this year where you need to know where these go in the circuit. Now that's the circuit. We've got a 9-volt supply, and really if we want to work out the resistance of this resistor, we need to use the equation that says R is equal to V over I. Okay, now this comes, you'll obviously be given your data sheet for GCSE. V equals I times R, but we've basically rearranged to say that if we want to work out the resistance of that component, we need to measure the potential difference across it, divide it by the current through it. So for a question like this for 4 marks, you're going to get a couple of marks maybe for drawing this diagram. You're going to talk about this equation, so you've got maybe 1 mark for drawing the correct circuit diagram. You're going to have maybe 1 mark for identifying which equation to use, and then you need to state the obvious things. So you could say stuff like measure the current through the resistor with the ammeter. That's a super obvious statement, but that is completely true. And often people forget the easy things because they're thinking about the harder bits of physics. You get lots of marks for stating obvious things. Just imagine you're writing for an idiot. Write down an idiot's guide to how to measure this. So measure the current with the ammeter. Then you can also say things like measure the potential difference across it with the voltmeter. Okay, so again, really simple stuff. All of you know this if you're watching this. But yeah, but I is just the current, it's the intensity of current, and V is the potential difference. Okay, so yeah, measure the potential difference across it with the voltmeter, calculate resistance by R is equal to V over I. Okay, so basically you're getting lots of easy marks for stating the obvious things. So that is as much of the live stream as I'm going to do today. I realise there's a question I haven't quite completed. So what I'm going to do is I'm going to complete this question, which is still about the experimental methods. There's something to do with different sorts of errors, working out the mean value, why V equals IR is not the same as Ohm's law. I'm going to continue with that question tomorrow, and then I'm going to go on to some paper 2 stuff. So basically that's where we've got to. That is the end of the GCSE part of the live stream. It's been amazing to see so many people out there. It's great to have so many people actually asking questions. I'm afraid I haven't answered them all. Abdullah, can 2 ammeters be added, 1 before and 1 after the resistor? Yes, if you did that, you should get the same reading on both ammeters, because the current is going to be the same everywhere in that single loop in that series circuit. Yes, why do we have I for current? It comes from the intensité de current from the French language. Oh yeah, and it's also great to see that so many people out there have actually sort of seen what I've been doing. I do have a newsletter. I did talk about the fact I was in Snowdonia at the weekend, did like a 58-kilometre hill run for about 13 hours, which was pretty brutal. But if you want to find out more stuff like that, I do have a newsletter. Just go to physicsonline.com and then you can sign up and you get updated with all the stuff that I'm doing. Okay, we're now going to start, Raven, A-level physics revision. So yeah, I've just done the GCSE stream. That's always going to be the first half an hour, roughly. And then the second half an hour, from sort of 8 until 8:30, I'm going to be doing stuff for A-level. Now, for those of you who've just joined, what I have is over on my website that hopefully you've had a look at, alevelphysicsonline.com. Let me just zoom in on this. So this is the website, and if you click this button up here that says live, it will bring you to this page. So you might be used to going to like the AQA page where you can find videos for the whole course. If you click on this live button, then it comes up with the live stream thing, which is where we are tonight. And you can see here that all the resources, the questions and so on will be kind of here for you to download. Now the questions tonight, because I don't want to be using like copyright restricted things, I'm going to be using questions from this book. This is one of my daily workouts. Hopefully you bought this book by now. If you're in year 12, then you should be working on book 3 before you go on to book 4. And the questions tonight are from book 3. So this is going to be AS Physics revision, and we're going to be looking at the double slit experiment. Now, in the start of my new book, so there's like a guide for all the questions. And what I'm going to do is I'm going to do some questions about the practical to do with the double slit. These are from the 3rd and 4th of March. And that means if you go to my website, you can download the questions. If you just click download now, and then that means you can see the questions for the live stream. And I'm going to be doing, and I am looking at the comments, there's so many things to talk about. There are so many questions that I'm going to be doing. I'm going to be putting up future questions for future live streams and so on. I will do more stuff with Astro. I've got videos about turning points for anybody in the chat. I'm going to be doing lots of stuff for revision, and I'm going to be covering some AS content and lots of stuff for year 13. So lots of kind of things, the kind of skills that you need. So these are the questions we're going to do tonight. We'll just see how we get on with them. Right, so let me just work out what we've got. So here we go. Got the questions here. So if you want to play along at home, then feel free to do so. The first one is something that everybody doing A-level physics should have done at some point. And looking at the questions, is this for OCR? This is for anybody doing A-level physics. So it's going to be useful if you're doing OCR, useful if you're doing EdXL, useful if you're doing AQA, and if you're doing OCRB, it'll be useful for you as well. Patel, if you wasted your Easter, don't think of it as wasting it, just think of it as having a good break, and now you've only got really 1 or 2 months of like super hard work. And everybody watching this stream can have a massive improvement over the next few weeks. Okay, explain the advantage of measuring the distance shown above rather than from one bright fringe to the next. So this first one, it's almost again kind of like common sense. If you had a ruler and you just measured from here to here, there's going to be a fair amount of uncertainty in that reading. But effectively, the more fringes you take the reading of, you're still going to have the same error. So say, for example, you're using a, they used a vernier caliper. So maybe the reading is going to be plus or minus 0.01 of a millimetre. Okay, so you're going to have the same error, but when you record the distance across more fringes, that's going to be a smaller percentage of that total distance. And therefore, you're going to reduce the percentage uncertainty, even though your absolute uncertainty is going to be the same. So the reason that we do it from here to here, you want to do it across as big a distance as possible. Now, the difficulty when you're actually doing this, and if you've been doing A-level physics, you'll realise that when you shine that laser through a grating or a double slit, when you have a double slit, because you've only got 2 holes for that light to pass through, not much light gets through, and the image you see on the screen is going to be really, really faint. And that's why you can't really measure any more than that, because they get too faint as you go further away from that central point. So, explain one advantage of measuring the distance shown above. You might say that it reduces, I'm going to go in blue, you might just say that it reduces the percentage uncertainty in the reading or the measurement. Okay, right. Some great questions, by the way. People asking about, are these about Olympiad questions? Yeah, it's difficult. Okay, when I spoke to some of the kind of top physics Olympiad students, even they found it really difficult. I don't think many people were getting high marks. But, you know, if you've had to go at Olympiad papers, the real exams are so much easier in comparison. Okay, we then need to complete the table of data. So we've got the distance from the slit to the screen, the distance measured, and then the fringe spacing. Okay, so how do we work this out? Well, basically, if we know we've got 1, 2, 3, 4, 5, 6. When they measured a distance of 1.14 millimeters, you divide that by 6 and you get this number over here. Okay. Now, as they move the screen further away from the double slit, that light is going to be spreading out more, so it's going to spread out more. So we're going to have a bigger measured distance. Now, when it's measured as 2.36, we're going to divide that by 6 because we've got 1, 2, 3, 4, 5, 6 fringes, and therefore all we're doing is we're taking this number here and we're dividing it by 6. Now here, I'm going to give my answer to 3 significant figures. Okay. Now we've got 3 significant figures in this data, and that means I'm going to give this data here to 3 significant figures as well. Okay. So hopefully that makes sense. And I think what I've tried to really emphasize with the book and the questions here is how important it is to be consistent with the number of significant figures that you're using. So we just do the same for the next one. So that's 0.62. Now that is not the correct answer. We've got that to 3 significant figures. That's to 2 at the moment. So we need to keep it to 3 significant figures. All of these are going to be to 3 decimal places as well at the moment. And therefore that's 0.62. We'd have 0.790. You'd have 1.00, and this one would be 1.22. Can uncertainties come up on any paper or only paper 3? Key, that's a really good question. I would say, I think they're mainly, if you're doing AQA, they're going to come up on paper 3. But the thing is, it's a skill that you should know about, and I think it's the kind of skill that they could potentially ask you about on paper 1 or 2 as part of another question. So I believe that if you're revising it now, you should know it before you do your first paper. But I think the main, if you're doing AQA, the main questions about uncertainties are paper 3A, which, by the way, you can buy extra practice papers for 3A in my shop. So a bit of a shameless plug. Go to physicsonline.shop. You can download 3 extra versions of paper 3A that I've written. But I reckon you should just know about uncertainties from now onwards, knowing that they could come up in any exam question. So all of these are to 3 significant figures. Okay, and that's why even these ones down here, I kept it to a different number of decimal places because they're still to 3 significant figures. The next part of the question is we have to plot that data. So we've got the distance to the screen. We've got the fringe spacing, which goes up to about 1.22. So when it comes to plotting data, generally in exams, they don't want you to plot too much because it's a time-consuming thing. Often they give you the axes pre-labeled. They might have 4 bits of data, and they just want you to plot 2 or 3. Okay, so right. So let's have a look at where we go to. So if that's 0 down here, let's say that's 0.2, 0.4. And again, if you want to play along at home, you can, of course, look at these questions. And what I'll do as well is I'll be putting a lot more stuff up online so you can look at future live streams and what I'm going to be doing. By the way, I don't have any predictions. I'm not going to get into that game. I've got practice papers for sale. I would never say they're predicted. I just reckon if you want to do well, you've got to learn the whole course. Students, in my experience, who are getting B's and A's and A stars, they're not hoping that some things are going to be predicted and they're going to come up and other things aren't. They just revise everything. So if you want to do well, don't bother looking at predictions, revise everything, because anything, in my opinion, could come up in future exams. Okay, so we've got these numbers here. We took this number here. We divided each one by 6 to get this because we had 6 fringes. And now if we just plot it, I really should be using I really should be using a pencil, but we've got 0.5, it's 0.19, so that's going to be about here. 1, we've got 0.393, 1.5 is 6.2. We've then got 0.79, which is there. 2.5, we've got 1, and then at 3, we've got 1.22. So what you can see, as you'd expect, is a straight line that goes through the origin. And that basically shows that the distance to the screen is directly proportional to the fringe spacing. We then should have a clear ruler. I definitely think a clear ruler is essential, and that means it allows you to see the points above and below the line. This isn't going to be great because I've blown this up to A3 and this isn't quite long enough. So we're going to have something that basically goes like this. Somebody says, do you know how to read a vernier scale? If you don't, then you should know how to read a vernier scale. It's the kind of thing that you can get marks for, and they're quite easy marks if you know how to read one. And I do have questions about that in my daily workout, book 1 and 2. So I've got lots of stuff there. I'll maybe do some questions about it soon. Okay, so we've drawn this. Now the next thing is if you're going to work out the gradient, then you need to use a ruler. Okay, now you want to draw a triangle which is bigger than half the length. Now for this one, I'm just going to do it in red just to make it clear. Again, it's super obvious, but make sure that you draw the triangle. Again, there's an easy mark you get in the exam. Now, okay, complete the table and plot the graph. So we've done that. Okay, right. Use this information about the separation of the slits as 1.5 millimeters and the gradient of your graph to calculate a value for the wavelength of laser light used. Okay, Rahik, please make another video with Z Physics about anything. Yes, I will do. I've got some videos planned actually about some Olympiad astronomy and astrophysics questions, so I've got those planned, but I need to get Z Physics in. He's an absolute top guy. He's, yeah, brilliant. I know he's going to be doing lots of good stuff this year, but yeah, hopefully I'll get some more videos with Z Physics. Okay, if the question tells us to draw a suitable graph and nothing else, do we draw a curve connecting the points or a line of best fit? I would say, drawing a suitable graph, you should draw a line of best fit, but that line of best fit could be a curved line. It depends on the data and what it shows. Most of the time, for A-level, they want you to draw a straight line, because once you've drawn that straight line, you're then going to use the gradient to calculate a physical value. Okay, so the gradient here, dy by dx, or the change in y with the change in x, is going to be equal to 1.0 minus 0 divided by 2.5 minus 0. And that's just going to be 1 over 2.5, which is 4.0 times 10. Hold on. One thing I haven't done is this is in millimeters and that's in meters. Okay. Now the gradient, we could give it as millimeters divided by meters, so that would then be 10 to the minus 3. But I can also convert this into meters. So we've got 1.0 minus 0 times 10 to the minus 3 divided by 2.5 minus 0. Okay, and when you do that, the gradient then is equal to 4.0 times 10 to the minus 4, and it has no units because it's the ratio of a length in meters to a length in meters. Okay. Okay, so we've got the gradient. Now, how do we use the gradient to calculate the wavelength of light? Well, this is what you want to be doing, is you want to be realizing that a gradient actually has a meaning, and it's going to relate to some real physical value. Sorry, there's somebody just spamming the channel, so I'm just going to hide them on the channel. Okay, so if we think about what we have with the double slit, we can say that the wavelength is equal to SW over D, or this thing here, the fringe spacing W divided by the distance to the screen is equal to the gradient. Okay, so if you want to work out the wavelength, all we need to do is multiply the separation of the slits, which was 1.50 times 10 to the minus 3 meters. We need to multiply that by the gradient, which is W over D. Okay, so the gradient here, it was equal to 4.0 times 10 to the minus 4, and then we can now do this in our head. So 1.5 times 4 is going to be 6.0. 10 to the minus 3 times 10 to the minus 4 is going to be 10 to the minus 7, which is then also 600 times 10 to the minus 9, or 600 nanometers. And that's the kind of answer that we'd expect, because 600 nanometers is in the kind of the range of visible light, and that's what we're using, because it says here that we're using a laser. And so 600 nanometers is probably going to be like a red laser light, and that's kind of what you tend to use in school because they're a lot safer than like the green or purple ones. So for this, to work out the wavelength of light, it's about 600 nanometers. Hopefully that makes sense. And hopefully you've had a go at doing this yourself. Now, of course, you need to know about a suitable method, about safety precautions of using lasers, but the double slit is quite important. But we can also do it again using other sorts of electromagnetic radiation. Just looking at the chat at the moment, it's great to see so many people on here at the moment. People asking, Mattia, what's your favourite equation? We've got 3 over 2 kT equals a half m CRMS squared. We've got somebody looking, Raven, at the drift velocity of electrons, equals mc squared. Oh, here we go, Albib. We've got something to do with Stokes' law and viscosity, where F equals 6 pi r NV, I think it is. Pi r NV, yeah. Also, pi, if you actually say it in Greek, the Greek way of saying pi is, I think, p, but we've always said pi, so we're saying it incorrectly in the Greek language. So cricket addicts, what topic for the next live? Do you know what? I don't know. I haven't planned yet tomorrow. So I reckon if you have any things that you'd like me to do tomorrow, put it in the chat, and that means I can make sure that I plan it accordingly. We're going to do a little bit more of double slit tonight. And what we'll do is I'll have a look in the chat, I'll see what people are asking about, and I'll try and pick some of those questions to have a go at for tomorrow. What formulas aren't on the formula sheet that you need to learn for the AQA A-level course? I think, to be honest, for AQA, pretty much everything is given to you. I don't think there's too many more that aren't on the sheet, but I did a video that I think is on my website, it's definitely on YouTube, where I went through the equations that they don't give you for A-level physics. So if somebody could find a link to that and post it, that'd be amazing. Okay, photoelectric effect, electricity and magnetism, electricity, medical physics, binding energy, particle physics, mechanics, nuclear physics, phase difference and path difference in their relationship. Yeah, Raven, that's a good one. SHM, yeah, so there's a lot of stuff here. I will be doing a lot of this stuff over the next few weeks. Right, so this is the double slit experiment, but on a much larger scale. Because in the last question we had light, where the wavelength is about 600 nanometers. We now have a microwave transmitter. These tend to have a wavelength of about 3 centimeters, which is why we've got 9 centimeters between these metal plates. That's 6 centimeters. So that means there must be a 3 centimeter gap here and a 3 centimeter gap there. And you get the maximum amount of diffraction when the wavelength is equal to the aperture. That's it. 42 equations you don't get in A-level physics. So that's the video I did where I talked about, 42 equations. They don't actually always give you, but I think are quite useful. Are these live sessions every day from 7:30 till 8:30? Yeah, 5 days a week. I'm not doing Friday night or Saturday night because you should be doing better things than watching me, but they're going to be every evening. Okay, determine the distance between the centres of the 2 slits formed in the experimental setup above. So the first question is basically like year 5 maths. So we want to know the distance between this centre and this centre. Now we already know that this gap here is going to be 3.0 centimetres. So it's going to be 1.5 centimetres from that edge and it's going to be 1.5 centimetres from that edge. So if you take our 9 centimetres, we're going to take away this 1.5, and we're going to take away that 1.5. That's equal to 6.0. So it's 6.0 centimetres. But again, what we tend to do in physics is give everything in metres. So I'm going to say that's equal to 0.060 metres. Okay, so if you're not sure, give it in standard SI units, and that means later on you've got less chance of forgetting to convert units in your final equations. And these questions are basically generic physics. So these, and I wrote these, and these are all in my daily workout books. So these questions are suitable for anybody doing any exam board. So AQA, OCR, Edexcel, Educast, WJC, SIA, CIE, Edexcel International. These questions are based on standard physics that everybody should know about. So it doesn't matter which exam board you're doing, this covers like the basics. Okay, the transmitter is set to 10 gigahertz, calculate the wavelength. So to work this out, we're going to go straight into the wave speed equation, V equals F lambda. Sometimes given as C equals F lambda. I think AQA sometimes just use C to be the wave speed, not just the speed of light. Raven, just wanted to say they did Edexcel paper 1, got an A. That's amazing work, that's fantastic. And thanks for using some of my videos to help you with that. Okay, so these are both the same thing, but I think AQA you tend to use C to represent the speed of a wave. I tend to use V equals F lambda. We want to know the wavelength, and that's just going to be equal to V over F. Now we know because it's a microwave, it must be travelling at 3.00 times 10 to the 8 meters per second. The frequency is going to be 10 times 10 to the 9 hertz. Okay, so basically we've now got something which is 3 times 10 to the 8 over 10 times 10 to the 9, and that's going to be equal to 0.030 because it's going to be 3 times 10 to the 8 divided by 1 times 10 to the 10, which is 3 times 10 to the minus 2. Okay, so for that question, you didn't even need your calculator. So that's the wavelength of the wavelengths of the microwaves, which tends to be the kind of things that we have in school. They tend to be about 3 centimetre long, 2.7, something like that, which again has links to the astrophysics stuff. And when we look at like the CMBR and the kind of the wavelength of this 2.7 Kelvin kind of radiation that's left over everywhere. Okay, coherent sources are needed to form a clear interference pattern. Define what we mean by coherent. So this is a definition, and it would be amazing if everybody watching at the moment just writes in what we mean by a coherent wave. All of you should know this. If you're in year 12, you should know it. If you're in year 13, you should know it as well. So what do we mean by a coherent wave? What would be the best way of describing it? So we've got a fixed phase difference, same wavelength and amplitude. That's a nice one. I really like that. That's the real Joe Linton. Is that the real Joe Linton? Constant phase difference is definitely a good one. Yeah, constant phase difference, same constant phase difference, same frequency. Yeah, if they've got the same frequency, that also then implies they've also got the same phase difference. So I would say coherent waves, they've got a constant phase difference. And I guess that kind of implies they've got the same wavelength and frequency, and also they have a similar amplitude. Okay, so I would say that the same amplitude, strictly speaking, I think I've often seen that defined, but I would say that the same or similar amplitude, because you know, if you had one which had a massive amplitude and the other which had zero amplitude or almost zero amplitude, you wouldn't see any kind of interference effects with them. But yeah, I reckon similar amplitude, constant phase difference, same wavelength. Monochromatic, I guess, yeah, monochromatic is good, but I would say it's better to say the same wavelength, because you might have waves which aren't coloured, as in they don't have any colour, so they might not be monochromatic in their description. So, you wouldn't say that X-rays or radio waves are monochromatic. So yeah, just 1 mark though for something like that. Okay, state the path difference and phase difference for the maximum constructive interference to occur. Okay, so when the path difference is, well, so basically what we're looking at is if you've got, say, 2 waves, then we're thinking about one wave being a bit like this, and then you've got another wave that is a bit like that, and basically you add them up and then their total amplitude gets bigger, so we get something like that. Okay, now for that to occur, the path difference must be 0, or it's going to be some multiple of the wavelength, so it's going to be equal to n lambda. Okay, so n lambda is the right thing. So when n is 0, then n lambda is just going to be 0. But if you were to take this wave and move it along by 1 wavelength, you then have 1 lambda. So n lambda is going to be when the path difference allows maximum constructive interference. Okay, hopefully that makes sense. Phase difference, well, it's going to be some multiple of 360 degrees. Okay, now the path difference is going to have units, or it's going to be measured in meters. The phase difference is going to be measured in degrees or radians. Okay, and so you'd have some multiple of 360 or some multiple of 2 pi if you're having that in radians. Okay, hopefully that's right. Okay, here we go. We've got some good questions over there. First of all, will there be daily streams, free maths lessons? Yeah, there will be. I'm going to be doing 5 streams a week. So Sunday night, Monday night, Tuesday night, Wednesday night, Thursday night, Friday and Saturday. It's not time for physics. This at the moment is A level. I'm going to be doing, I think it says beneath, GCSE or indeed IGCSE is from 7:30 till 8:30. And then A level is from sort of 8 o'clock till 8:30 or a little bit beyond. Other questions people had, would this question here be 1 or 2 marks about phase difference? I think in the exam this would be a 1 mark question, but you want to make sure that you do say it's got a constant phase difference with the same wavelength and a similar amplitude. If you do that, I reckon that's enough to get you that 1 mark. Maybe it might be 2. It's some weird actually, it's how I've looked at loads of past papers, and when I've looked at definitions, some years that definition has been worth 2 marks, and another year or a different exam board, that same question for the same definition has been worth 1 mark. I think it really depends on how many marks they need to fill up the rest of the paper. Okay, right. Should we do the rest of this today, or should we leave it for tomorrow? Right. So I said 8:30. Do you want to go on a bit longer? Let me know. Yes, you want to do now. Oldman. Yes, you want me to do more physics. We can continue. Yeah, today, Tommy, Afsar Khan, today. Okay, right, I'll do it. Okay, so the next question. The receiver is initially positioned to detect the central maxima opposite the transmitter. Then it's moved along the line away from the centre. Then it goes down and goes up. Okay, so basically what we're saying is at this point here, I was going to do this in green. We're basically saying that at this point here, when it's perfectly in line, we're going to get a maximum value. Okay, you then move it away, and there's going to be a point where we've got diffraction of waves from this gap, and you've got diffraction of waves from this gap, and there's going to be points where we have constructive interference, and then we get a maximum signal, and then we have other points where you've got a trough and a peak meeting, and we get maximum destructive interference. So you might move from here, you might go to a minimum position, and then as you move it further along, we get to another maximum. Okay, so we're saying that over here, we've got another maximum position. So, calculate the distance to this first maximum from the initial position. Now this is basically, we're going to use the same equation that we used earlier, which basically says that the slit separation, the fringe spacing is equal to the wavelength times the distance to the screen divided by the slit separation. Okay. Now normally we're really used to using this equation when it comes to looking at light. Here, the fringe spacing is basically going to be from a maximum point to another maximum. So this distance over here, I'm going to label as W. Okay. The slit separation, S, is this distance over here between the centre of these. So that's our distance, S. D is going to be this distance over here. So that's D, which is 1 metre away. So that's D. So again, always circle stuff, you know, add stuff to your diagrams. We want to know the distance to the first maximum. So that's going to be equal to the wavelength, which is what we calculated over here, as 0.030 times 1 metre to the screen. And the slit separation is 0.060. So basically we've got 0.03 divided by 0.06, which is going to be basically a half, times 1, which is equal to 0.50 metres. Okay, there we go. A-level physics. You don't even need a calculator. I gave that to 2 significant figures, by the way, because the distance to the screen was also given as 2 significant figures. So that's why I gave my final answer as 0.50 metres. So basically, you take that receiver, you move it half a metre along, and it goes to another maximum value. Okay, so what he says, isn't n lambda d sine theta? Cricket addicts, that is the equation for a diffraction grating, not a double slit. And that's why I'm using this equation here to do with double slits rather than for diffraction gratings. Also, I think this is often sometimes given as lambda equals ax over d or something. So this is like, I think, the OCR version, but there's like a, I think OCR and edX, I think OCR and AQA have a slightly different equation for this. Has the TikTok live dropped out? Callum, do you know what? Okay, is that working? Okay, I've actually got my old phone here, just doing a TikTok live. People on TikTok, hope all of you are doing okay. You can obviously see the whole thing on YouTube, so I'm just going to put that up there. I think my phone is about to die from the battery. Oh yeah, so for OCRB, it's lambda equals AX over... Sorry, for OCRB, it's... Well, I'm just going to write this down from the chat. Right, so we've got... lambda equals AX over D. This is AQA. For somebody there doing OCRB, they've got lambda equals XD over L. Yeah, so there's all sorts of different things. It doesn't really matter. Basically, you will be given that in your data sheet. You'll have learnt how to use it. And then whichever course you're doing, it doesn't really matter. This is just the way it's presented. Do you need to know the derivation of that? I believe, Jamil, that you do for AQA. And I do have on my website derivations. Yeah, so if you want to find the derivation for that, I've got it on my website. So I think, let me just have a look. Right, so looking at A-level physics online, if you go down to the bottom of the page, you can find lots of useful stuff. Now I do have here derivation sheets. Now, oh, you need to kind of be a member, but that's fine. Let me do that. Do you know what? I'll do that tomorrow in the stream. But basically, I've got derivation sheets where I have all of these, and you can download them and just learn them. Okay. When the receiver is moved along the line away from the centre, it detects the second and then the third position where the signal strength is at a maximum. Calculate the angles where these two maxima are detected. So basically, we're going to move this along. I'm just going to draw it really simply here. So we've got effectively the 2 slits here. We've got a maximum point here. Then it goes to a minimum, then a maximum, minimum, maximum, minimum, maximum. Okay, and basically, if this is like the central one, we've got the first, second, and third. And what we're trying to do is calculate either this angle, or we're going to calculate this angle over here. Now, in order to work out that angle, we need to know this side here, and we need to know this length over here. So effectively, if we think about this being a right angle triangle, we've got the adjacent side and the opposite side. And then if you know the adjacent and the opposite, we can use tan is equal to opposite over adjacent. So how do we work out that? Well, basically, the way I'd say is we want to draw some simple pictures. So for the second order, we know that the distance between the double slit and the screen is going to be 1.0 meters. We also know that if the maximum is 0.5 of a meter away for the first maximum one, for the second maximum reading, well, that's going to be equal to 0.50 plus 0.50. So that's going to be a total of 1.0 meters. Okay, so we've got a right angle triangle. That's a meter. That's a meter. And that means without doing any maths at all, this angle in here is going to be equal to 45 degrees because we just have a right angle triangle where both of these are the same. And at the moment, we're doing the double slit experiment. Okay, 45 degrees, O's covers, perfect. For the third one here, again, it goes along a meter, but now it's going to go up 1.5 meters. Okay, because again, it was 0.5 of a meter to the first maximum. The second maximum is going to be 1 meter. The third maximum position is going to be 1.5 meters. And now to work out the angle theta, theta is going to be equal to inverse tan of 1.5 over 1, which is just 1.5. And if you put that into your calculator, we find that theta is equal to 56 degrees. Okay, so there we go. Isn't there a maximum in the middle? Yes, there is. Yes, so there's, sorry, we've got like the 0th maximum. We've got the first, second, and third. But we're going to get like the biggest signal in terms of the amplitude in the very dead centre. Because as these go further away, there's going to be more sound, more of the microwaves going to be sort of lost to the surroundings. So there's a maximum in the middle, and then it goes min, max, min, max, min, max. Does that make sense? Hopefully it does. Now, of course, if anybody out there has kind of missed any of the live stream, you can review everything just by going to my A-level site. I'll put up this stream afterwards so you can find everything that you need. If, of course, you like these questions and basically you want to do more stuff like this, I guarantee if you buy this book and you do all of the questions, you will get better at physics. That's my guarantee. Also, for the questions, all the answers are in the back over here, so you can find all the answers to all of the questions. But of course, you know that I'm not just like other people. I do things for you that other people aren't doing. And if you go to alevelphysicsonline.com, if you go to books, you'll then find I've got my daily workout books 1, 2, and 3. If you click on book 3, it takes you to the page. And if you view work solutions, what I have for all of these books are the answers explained. So you can either just download it. So if you want to just look at a downloadable set of answers, which are a little bit neater than the kind of stuff I've done tonight, you can see that we've got the answers from tonight and the questions that we've just done. So you can see all of my answers are here. So that's W plus W and that's W plus 2W. So a lot better than I've explained it tonight. And also, there's also a video of this as well. So if you want to look at just this video, you can, it's a little bit slow, but if we go to the chapters, you can basically, on this, when it does load, I don't know why it's being a bit low, you can basically find work solutions to the whole month. So if there's a question that you don't understand, then you can always, obviously this isn't a great demo when it's not quite working, but let's just refresh that. You can basically watch a video where I go through questions for the entire month. So it means that you can basically teach yourself A-level physics. Look at that. It's like book 3 with my hands on there. And you can hopefully see that I've got every answer there. Oh yeah, the book's, sorry, it's £9.99 on Amazon. If you buy it tonight, you'll probably get it by Wednesday. It's not AQA certified, But I know that Edexcel and OCR recommend my resources. Yeah, how do you practice more Unit 3 uncertainty problems? It's difficult. Okay, are these similar to exam level difficulty? Yes, I reckon if you do all the questions here, that's kind of going to get you to like the sort of C, B, A grade boundaries. If you want to kind of get an A or an A star, I do have some extra practice papers and other bits and pieces. Right, okay, so Rasif, good luck in your physics undergraduate classical mechanics exam tomorrow. Wow, that is like another step above A level, isn't it? So I hope everybody watching this is doing all right. For everybody out there, please buy some of my stuff, it really helps me. But of course, I will be back again tomorrow night. I'll put some stuff up in the morning tomorrow about what's going to happen, but it's going to be 7:30 for GCSE, 8 o'clock for A level, and I'm going to be doing a lot more over the coming weeks. So thank you, everybody, and see you soon. Bye.